All right, welcome to week two's presentation about Newton's second law by me, Coach Davis. In this presentation, we're going to talk about some big ideas, force, mass, acceleration, how they are all working together in Newton's second law, some real life examples, a little bit of math, and a summary. So let's knock this out. The big idea. For the next 2 weeks, we're talking about Newton's second law, which pretty much explains why some things speed up or slow down different than others. We're going to be talking about force, mass, and acceleration. And combining these together, force, mass, acceleration, we actually create a math problem known as Newton's second law, which is force equals mass times acceleration. It helps explain the universe and how some things speed up or slow down differently than others. Just a quick review, force is a push or a pull on an object. So anytime you push on an object, you're applying a force, or if you're pulling on it, applying a force. There is these things in science known as units. There are these letters that go after these numbers to let us know what we are looking at with these numbers. So for this case, that would be newtons. So if we had 72 in, that would mean 72 newtons. Capitalization does matter, so keep that in mind. Examples, if you open up a door, if you're pulling on a backpack, or you're kicking a ball, you are applying a force, either a push or a pull. Mass. Mass is the amount of matter in an object, and for this class, for at least right now, the more matter something has, the more likely it is to not want to stop moving or to not start moving. Its unit is known as the kilogram, which is lowercase k and lowercase g. So just a reminder, if you see numbers in a science class, it should probably be accompanied with a unit. And if it happens to be mass, it's kg. Examples, bowling ball versus a soccer ball. A bowling ball is going to have more kilograms than a soccer ball because it has more matter. In other words, more stuff that makes it up. Acceleration. Acceleration is a change in motion. And when we think about acceleration, we think generally about something speeding up. But technically, acceleration also means slowing down and changing direction. Used in an English class or everyday vernacular, we're gonna mean speeding up. But in a science class, you should know it also means to slow down and change direction. The units for this is kind of weird. It's meters per second per second. Per, by the way, means to divide, so meters divided by second. And so here's our unit. This one's the easiest one to type on a computer, and you're more likely to see this one in my class. But if we're working on paper, meters per second squared, you're going to see this one, because this just happens to be one less character you have to write. If you open up a physics textbook, you're probably going to see this one. They're the same exact thing, so don't let that freak you out. It is a weird unit. Meters divided by seconds again. An example, a soccer ball is going to accelerate more quickly than a bowling ball with the same amount of force applied because the soccer ball is lighter, and that's what we're kind of getting into this week. So, some real life examples. Say you have an empty shopping cart and you give it a little bit of force. It's probably going to accelerate. But you have a full shopping cart and you give it the same amount of force, it's not going to accelerate, or it's not going to accelerate nearly as fast as the empty shopping cart. This is simply because as you increase the mass, to accelerate it at the same speed, you're going to need the same amount of, or you're going to need more force. Example 2, a broken down car. If one person tries to push a car by themselves, it's probably not going to be enough force unless you are a super strong, really big individual. But if we get a few people, like 5 or 6 people, to try to push a car, we could do it because it's a lot more force on a really big mass, and then we'll cause it to move. So more force is required when things have a lot more mass to cause acceleration. Last example, example 3, kicking a soccer ball versus a bowling ball. If you are to kick a soccer ball, it's going to have quite a bit of acceleration, especially if you kick it as hard as you possibly can. It's probably going to go flying 50, 60, 70 feet, yards. Whereas if you were to kick a bowling ball with that same amount of force, first off, your foot would be probably broken, and second, it's going to hardly move. That's because the bowling ball has way more mass than the soccer ball has. So when it comes to units, I kind of pointed this out earlier. Units are super important in a science class. Without units, your answer is simply wrong. And so force, just a reminder, is the letter N. So if you see 5 in a science class, it's probably going to have a unit. So like 5N. Mass, this would be kilograms. So a good example of that would be 1 kilogram. Acceleration is 5 meters per second squared. Now note, there's always a space in between these. One of the biggest mistakes I actually make is not putting a space here. It does need a space. Another big mistake that I see out of students is not learning these. So you might take a second, pause this video, and memorize these 3 things because it's going to help with the math and passing the upcoming test. Got it? All right, let's roll on. So when it comes to math, and I can already hear the groans right now, some people going, oh, this is a science class, why are we doing math? Well, because science involves quite a bit of math. There's actually a pretty quick way to do this algebra in Newton's second law, and it involves this triangle right here. So here are the 3 steps. Number 1, you should read the problem. Number 2, figure out what you're solving for. And number 3, cover up what you're solving for on the triangle, and the triangle will just tell you what to do. So if I'm, say, solving for force, then I'm just going to multiply mass times acceleration. Say I'm solving for acceleration, I'm just going to take force divided by mass. And if I'm solving for mass, I'm going to take force divided by acceleration. Just cover them up. So let's give 3 of these problems a quick try. Step 1, read the problem. A soccer ball has a mass of 2 kilograms and an acceleration of 4 meters per second, or 4 meters per second squared. What is the force applied? Next up, look at what we're trying to solve for. In this case, it's force. So we're going to cover up force right here, and we know we just need to multiply mass times acceleration, which is pretty easy. That's going to be 2 times 4. So 2 times 4 is 8 newtons. 2 kilograms times 4 meters per second squared equals 8 newtons. Not too bad. Let's try it again. So a force has 20 newtons. A force of 20 newtons makes a cart accelerate at 4 meters per second squared. What is the mass of the cart? Okay, well, we know we need to solve for mass. So we're just going to cover up mass over here, and we're going to take force divided by acceleration. So 20 divided by 4, 20 newtons divided by 4 meters per second squared equals 5 kilograms. Not too bad. Let's try one more. A person pushes a box with a force of 30 newtons. The box has a mass of 10 kilograms. What is the acceleration? Well, there it is, what I'm solving for, the acceleration. And then I'm just going to cover that up, and it's going to be force divided by mass. So there's my force, 30, divided by my mass, 10. So 30 newtons divided by 10 kilograms equals 3 meters per second squared. That's the math. It's just covering up the triangles. Now, there is a little bit of relationships with this data that we're going to be looking at. The first relationship is a direct relationship. The more force you have, the more acceleration you're going to have. So if we keep mass completely the same, 5, 5, and 5, but we increase the force, 10, 20, 30 newtons, what we're going to see is the acceleration is going to go up. So as force goes up, acceleration goes up. That's a direct relationship. 10, 20, 30, going up. Acceleration 2, 4, 6, going up. Direct relationship. Now the opposite of that is known as an inverse relationship. Say we keep the force exactly the same. Same push every single time. 10 newtons, 10 newtons, 10 newtons. But we increase the mass from 1 kilogram to 2 kilograms to 3 kilograms. The acceleration is actually going to go down. 10, 5, 3.3. They're just going to go down. So as the mass is going up, 1 to 3, the acceleration is going down. This is an inverse relationship. So quick review. Direct relationships on graphs, they go up. And if you're looking at a table, the numbers are going up too. 10, 20, 30, 2, 4, 6. With an inverse relationship, one is going up, mass, 1, 2, 3, but another one's going down, which is acceleration, 10, 5, 3.3. So direct relationship, both go up. Inverse relationship, one goes up, the other one goes down. This is Newton's second law, kind of glanced over everything. It's really just pushes, pulls, and kicks, and mass and acceleration. That is it for this presentation. Best of luck. Make sure you take the quiz that goes with it. Adios.